The objective of this video is to develop loss calculations in the windings of AC machines. And when we talk about losses in our machine windings, we can talk about three primary sources, which, depending on how you look at it, are really the same thing. But I've differentiated this as three sources. The first is something I'm calling DC losses. And DC losses are the normal losses you think of in a resistor. They are your I squared R losses. So if you've got a current I going through a resistor of value R, you get I squared R power loss. If that current is AC, you have I squared R, where I is the RMS quantity. The second category is AC or skin effect losses, and this is due to the skin depth of the material. That is, if you have a material that's exposed to a time-varying current, it will only use a portion of the conductor to conduct that current, and that portion is the skin depth. And so effectively what happens is that you have a higher resistance because you're using less of the conductor's surface area. And you can model this by simply a correction factor multiplied by your I squared R DC losses. A way to mitigate the problem is to use thin enough gauge wire for the frequency of currents that you're using so that the skin effect is negligible. That means that the entire cross-section of the conductor is effectively used. And mostly when we'll be considering losses in our windings, we're going to assume that we're using a thin enough wire so that we don't have to worry about the skin effect. The third category is called proximity effect losses. And these are losses due to external magnetic fields cutting into our conductor. So if a time-varying external magnetic field crosses our conductor, it's going to induce an eddy current, which will create losses. And these externally produced fields might be produced from a neighboring conductor next to the conductor that's experiencing the loss. So if you have, for example, your stator winding has multiple conductors packed into a slot, and the field produced by each of those conductors will cross over another conductor and create losses, and that's kind of the classical proximity loss scenario. But another case is the motor's magnetizing field may also cross your conductors and create losses. So chapter 5 of your book presents a detailed set of calculations for all of these phenomena. We're going to focus this video on the I squared R losses and mainly how to calculate your resistance of your winding. And so the rest of the video is going to focus on how you calculate resistance for a coil. And well, resistance is a pretty easy expression. It's just going to be equal to the length of your conductor divided by the conductivity times the cross-sectional area. And so we can say that the overall length for our whole coil is going to be ZQ, where ZQ is the number of turns that are in series, times the length of a single turn, the mean length of our coil, and then of course divided by conductivity and times the area of a conductor. So the real question in all of this is, how do you calculate LC? The rest of these parameters are pretty easy to determine. You already know from your winding design the value of ZQ. Conductivity, well, that's just going to be based on the material that you're using. So if you're using copper, you'll look up the conductivity of copper. The area of the conductor, that's the cross-sectional area of the gauge wire that you choose. So you might choose 18 gauge wire that has a certain cross-sectional area, or maybe it's 16 gauge wire or 20 gauge wire. But whatever it is, all of these parameters, ZQ, sigma, and ACON, you know immediately. But LC is a little bit tricky. So actually, we're going to focus on how you calculate LC. And I'm going to do this by trying to sketch for you a series of drawings for what our coils look like on our machine. So first, let me sketch a 3D view of a stator that's been unrolled so it looks more linear and is easier for me to draw. So here we've got our stator. And we're going to say that we've got a coil that has a span of 3 slots. And so our coil loops around these slots ZQ number of times. And if it's a double layer winding, it starts in the top layer and it connects back to the back layer. And so it does this many times over and over again. And the question is, what is the length of a mean turn? What is the average length of the turns? And so what we can do is we can extract this coil out over here, and we can draw it as a 2D view. And we can try to divide it up into regions that we can make calculations for the lengths. This region right here is the region that resides in our slot. And that has a height that's the same as the vertical height of our motor, the axial length of our motor, L. So that's a pretty easy calculation. That's the part that we know pretty well. We've got a portion of our coil that resides within the slot and has a length L. The real question is, what's going on at the top, which would correspond to this right here. Oops, I'm going to highlight this in a different color. What's going on in our end connection regions? So in green, we've got this up here, and then in blue, we have these bends where the coil arcs out of the slot and back into the slot. So how can we estimate these lengths? And that's what we're going to be talking about here. Okay, so I've sketched a 2D view looking down at our coil from up above. So that is, we've got our 3D view here, and we're staring down, and this is what we would see down here. And what we're trying to identify from this diagram is this green swath. And what we're going to do is we're going to divide it up as the region of our coil after the coil has bent around to travel circumferentially. So we're specifically sectioning off this area, which is this up here, and we're going to mark it as this length right here. And we're going to express this in terms of our slot pitch. So I'm labeling this as tau u, that is our slot pitch. And if you'll recall back to the parameterized stator that we looked at in homework 2, we had labeled the height of our tooth as dst. And so we're going to evaluate our slot pitch tau u, our slot pitch, at half of our tooth height. So we're going to evaluate it in the center of our tooth so that we have the right radius. And we can calculate tau u as being the slot angle times the radius of our slot, and it's that radius that we're taking to be right here, halfway back in our tooth. So tau u is our slot pitch, and it's in units of meters or millimeters. It's not an angle, but rather it's a linear length. So it's the actual linear length that I've labeled on here. And so we can make the observation then that this length right here is going to be tau u times the number of slots that our coil spans minus 1. And so if we're spanning one slot, this length simply doesn't exist. That would be a coil that is wrapped around a single tooth like this. So all that would exist would be the blue areas, the areas where the coil is bending. That's what our modeling assumption is anyway. And finally, we note that we actually have multiple coils in these slots. So this brown coil has to be placed so that it doesn't interfere with the purple coil that I just sketched on. And to account for that, we multiply this by a fudge factor, which we call KOV. So this is this is a factor due to increased length of coil to accommodate end winding overlap with another coil. And typically KOV is between 1.6 and 2. And I'm going to be posting a paper on Canvas that you can take a look at, which this KOV value, they summarize this range of 1.6 to 2, and they've extracted it by experimental results. That is, they've actually taken a look at a bunch of motors, and they've measured KOV. They've determined that it's typically between 1.6 and 2. And so because we don't know any better, we're just going to blindly assume that it should be 1.8, so the average of these. You might have better knowledge for a specific design that you should assume a larger or a smaller value. So that answers, we've got now two of our lengths. That is, we've got the green region up here, And we've got this region as well defined. Now what we need to do is figure out what the length of these arcs should be. And we're going to do this by just sketching a coil that has a span of only one slot. So that is a concentrated coil. And so if we do that, we can model the end connection as a half circle. So we've got this half circle end connection, and that means that it has an angular span of pi radians. And what we're trying to determine is what this linear length is of this connection. And we'll call this LA. And we'll do that by assuming a diameter of this coil. And we're going to take the diameter as being the average of the width of our tooth and our coil span. So if we label on here, and again this WST is something that we've labeled in the parameterized diagram that you received in homework 2. And the reason that we're taking it as the average of these two is to acknowledge the fact that our coil placement in here shifts a little bit based on how much of the slot space our tooth takes up. And so this is just a way of modeling this. Again, this is an approximation. We're just trying to come up with some framework that we can use to calculate these lengths so that we can evaluate the impact of changing our machine geometry in terms of the losses of our winding. So if we have a thicker or a thinner tooth, that has implications for the resistance of our coil, and we want to have a model that captures that with reasonable accuracy. So if we make this modeling choice that this diameter right here is going to be the average of WST and tau u, now we can calculate the length LA. So the linear length is going to be the angle times radius, and angle is pi, and radius is this divided by 2. And so we can take this LA value and we can go back up to our diagram over here, and we can note that these lengths right here are LA divided by 2. And we're now in a position to calculate our total coil length. The length of our coil is going to be 2 times these regions, 2 times our active length, plus 4 times LA by 2. We have 4 regions that have length LA by 2 within our coil. And then we have 2 regions that have a length of KOV times tau u times y minus 1. So we now have the total length of, or the average length of a turn in our coil, and we can use that in this expression up here to get the resistance of a coil. And then we can go back to our winding schematic, our winding diagram layout, and determine how our coils are connected to get the complete resistance of a total phase winding. And when we have that, we can calculate our phase winding losses as I squared R. If we have skin effect, then we can modify that to account for skin effect. And separately in your book, you can learn about how to calculate proximity effect losses. And I'm also going to be assigning some reading material that deals with this. But our focus in our modeling is going to be on I squared R losses of our machines. So in summary, this video has developed loss calculations for the windings of our machines, and we've primarily focused on how we calculate the length of a coil of our machine in order to calculate the resistance of the coil. And we've based this off of physical drawings of how our coils are placed in the slots in order to capture the effect of our tooth thickness and our slot pitch on the resistance of our coils.